Today we're going to be talking about transfer learning, which we didn't quite have time to get to last time. And in particular, we'll talk about the problem formulation and fine-tuning, which is a very successful and popular approach to transfer learning. And then we'll start diving into meta-learning. We'll talk about the problem formulation, a general recipe of meta-learning algorithms, one class of approaches, which I call black box adaptation approaches. And if time, we'll also go through a case study of GPT-3, which can be viewed as a black box meta-learner. And then by the end of the lecture, hopefully you'll be able to understand the differences between multitask learning, transfer learning, and meta-learning, some of the basics of transfer learning, as well as the training setup for few-shot meta-learning algorithms and how to implement black box meta-learning techniques, which you'll be doing in the first homework. Great, so let's get started with transfer learning. So recall last time we went over multitask learning, and the goal of the multitask learning problem is to solve multiple tasks at once. So you have some number of tasks, maybe T tasks, you have a data set for each task, and you're trying to learn a single model with parameters theta that can solve those tasks. And some of these parameters might be shared, some of them might be actually not shared across tasks. The goal is just to be able to do well on the different tasks, on all the tasks that you're given, given the data set. Now, what does transfer look like? What does transfer learning look like in comparison to this? So the goal of transfer learning is to solve a target task, which I'll denote as task B, after solving a source task, task A. And in particular, the goal here is to kind of transfer some knowledge that you learned, that you kind of acquired when learning task A, when trying to solve task B. And one kind of key assumption that transfer learning methods typically make is that you can't actually access the data for task A during this transfer process. So you basically have to learn something about task A, then you can no longer access that data, but you can access the knowledge that you've learned when trying to solve task B. And so transfer learning is actually a valid solution to multitask learning. You could learn one task and then learn the next task, but not vice versa, because multitask learning assumes that you have all of the data available when you're solving them. So a question for you to get started for today, you can answer in chat or raise your hand. What are some problems or applications where transfer learning might make sense, but where multitask learning might not make sense? Any ideas or thoughts?
I'm sorry, yeah, I actually had a question. So can you use the data from task B, or is there just no data at all?
You can use the data from task B. So kind of specifically, you assume that you've learned something about task A, you have that knowledge, and then you also have a data set from task B, and you want to leverage both your previous knowledge and the data from task B to learn a model for task B.
Thank you.
Training a robot to follow instructions in one house and then getting it to follow instructions in another house.
Yeah, that's a good example. So maybe a robot has learned to do one task in one house, and now you want to kind of transfer what it's learned to that towards a new task, but you don't want to have to kind of retrain it on that previous house. You just want it to do well in the next house. Do you also have thoughts?
Yeah, I was going to say something similar, transferring a robot in a simulated domain and then transferring over to a real-world domain.
Great, yeah, so maybe you've trained something in simulation, you've learned something about kind of physics or how to perform a task, and then you want to kind of leverage that knowledge when learning something in the real world, but maybe you don't want to have to retrain on simulation throughout the process because you really care about learning something in the real world and not learning something in simulation. Looking at the chat, there's also some thoughts about kind of transferring from one hospital to another hospital when you're looking at kind of medical data. You may not be able to access the previous hospital's images, but you want to be able to kind of leverage what you learned there. Also, things like transferring from learning a simpler task like picking up a block to a harder task like picking up an irregular shaped object. personalization. Personalization will actually, I think, actually falls well within the meta-learning context, and we'll potentially talk a bit about that later. Yeah, and then another example is when you have a small amount of data for task B and task A and B are similar. Also image style transfer and some other settings. So these are all good examples. And then, yeah, another example is like maybe you don't have you've kind of limited compute power, and so you don't want to have to keep on training on task A when transferring to task B. So yeah, what I wrote on the slide first is kind of something that you guys came up with, which is if this data set DA is very large and you only have kind of a limited compute budget, then you don't want to have to retain and retrain on that data set when transferring to the second task. Another example is when you don't care about solving both task A and task B simultaneously, you only care about really the thing that you're transferring to. The sim to real example is like one good example of this, where you don't really ultimately care about getting a policy that works in simulation. You care more about solving the target task. And in this case, it's fine to kind of discard what you had learned from task A and just try to use that knowledge when learning task B. Okay, and then also I guess one thing that isn't here is if there's some issue with kind of being able to access the data set from task A, then this is also a scenario where that might make sense. Okay, yeah, and then there's also a question in the chat about, is there any kind of differential privacy concerns when it comes to transfer learning, or is inferring the data to train the neural network difficult enough to render this irrelevant? This is actually a really good question. If one of the reasons why you're using transfer learning is because you have to throw away your data set DA, because you just like for privacy reasons or something else, then there are potentially concerns about, well, maybe you're throwing away the data set A, but you're still retaining the model that was trained on DA, and you may actually be able to reconstruct the data in A and private information in A from that model. And so in those contexts, when you do care about privacy of things in the source task, then you do want to think about whether it is actually possible to reconstruct that data from the model itself, and think carefully about that. Okay. So this is kind of the transfer learning problem statement and how it differs with multitask learning. And really the most prevalent approach to transfer learning is something that's called fine-tuning, especially within neural networks and deep learning. So the way that fine-tuning works is you assume that you have some set of parameters that are pre-trained on a data set, the source data set DA, and then you run gradient descent using the training data for the new task B. So this is kind of the data corresponding to task B, or at least the training data corresponding to task B. And typically you don't just run one gradient step, you typically run many gradient steps on this new task or this new data set. So that's it. It's quite simple, and it actually works quite well in a number of different instances, especially when there's a lot of kind of rich information and knowledge in your source data set DA. So for example, if you pre-train on ImageNet, this is what this kind of row is right here, and then fine-tune on the Pascal data set and the Sun data set, you get, these are kind of other image classification benchmarks that are a bit different. You get 58% and 52% accuracy respectively, whereas if you instead initialize your network weights randomly, you get 41% and 35%. So essentially all of the knowledge coming from ImageNet is quite helpful for getting a higher accuracy on these downstream data sets in comparison to a randomly initialized neural network. One question is, well, okay, say I want to have some downstream tasks that I want to be able to transfer to. What are some good data sets for pre-training, and where might I get pre-trained parameters? ImageNet classification has been one that's kind of been proven time and time again that's been quite helpful, especially for downstream image-based tasks, even when your target task is not actually a natural image classification task. So people have shown that ImageNet classification has been helpful for depth images, for example, and other kinds of non-natural images. Another kind of popular example for pre-training is using models, language models that are trained on very large language corpora. Examples of this are BERT and language models, and we'll kind of show some results on that on the next slide. And then another kind of just generally popular, especially actually popular maybe in the 90s or so, was actually to use unsupervised learning techniques to get pre-trained parameters and then fine-tune from that. Unsupervised learning techniques like autoencoders, for example. And really just kind of whatever large and diverse data set you might have lying around can be quite helpful for pre-training when you want to transfer the information in that large and diverse data set to your downstream task. Lastly, a lot of these pre-trained models are often available online, so you don't actually have to even download the data set and train on that data set. You can typically just download a pre-trained model from the internet and then fine-tune that model on the task that you care about. Okay, and then fine-tuning in general is a bit of an art. There's a lot of different design decisions that go into it with regard to which weights you choose to run gradient descent on, how you set the learning rate, and so forth. And unfortunately, there hasn't really been any kind of science behind what happens when you choose these different design choices. But there are some common practices. So it's common to fine-tune with a smaller learning rate so that you don't kind of destroy what is in the pre-trained network with a larger learning rate. It's also common to have a smaller learning rate for the earlier layers, because often the earlier layers in the network have more general purpose features like edge detectors in an image classification network. It's also common to even freeze earlier layers, setting their learning rate to 0, and then potentially gradually unfreeze them until you once you train the later parts of the network effectively. Sometimes you also reinitialize the last layer if you want that to kind of learn quickly and adapt quickly to your new task. And then in all of these cases, you can search over these various design choices and hyperparameters with cross-validation on your downstream target task. And then finally, different architectures matter a lot. So for example, a network architecture called residual networks or ResNets tend to fine-tune more quickly, simply because it's easier for gradients to pass through all of the network compared to some other architectures. Okay, so any kind of questions on this, on kind of fine-tuning and how it works? There's a question from, is pre-training in an unsupervised learning setting performing better than ImageNet? This is a good question. I think that in general, as of a year ago, I know that ImageNet was doing better. I know that people have been really actually most recently pushing on unsupervised learning techniques and also what's called semi-supervised learning. In general, I think that ImageNet has been more successful, but I think there have been some recent results that have shown promise in unsupervised learning approaches approaching pre-training on ImageNet. You have a question?
Yeah, can you talk a little more about search over hyperparameters? How would we do that in practice?
Yeah, so one kind of one kind of reasonable way to do that in practice is to choose some hyperparameters that you think might be reasonable, try them out, run fine-tuning with those hyperparameters, and then see what the validation performance is on a held-out validation set for some different choices. Then for the choice that works the best, you either choose that or maybe refine them even further. There are also more automated techniques for this, such as grid search, random search, where you kind of sample values within some range for all of the hyperparameters. And that can, if you have a fair amount of compute, then that can also be an effective way to choose hyperparameters. And then lastly, there's also techniques in Bayesian optimization that try to optimize the hyperparameters for you. I'm not sure if I pronounced that right.
Yeah, you got it right. So I have this basic question about transfer learning. So some of the examples make sense. So like on the language corpora, one language has it, and then do transfer learning on the other language. but some of the examples previously stated, like robot motion in one setting versus the other, how do I think about transfer learning versus generalization? Because like in that case, couldn't I also think that if my model was, generalized enough, that it would be able to learn in a different setting, and I shouldn't need to fine tune my last layer or.
No, that's a good question. So it's possible that that the network, the parameters data themselves will just generalize to a new setting if your target task is close enough to the task that you pre-trained on. And if that is, you could just kind of just test it and see if it works. And if it works, then you don't actually need to do any fine tuning. And that's what's called zero-shot generalization, in the sense that you're basically generalizing to this new context without any new data points. And then if that doesn't work, then fine tuning is usually kind of the next step that you can use to try to be able to do well in that new setting.
Gotcha. Thanks.
So this is, I guess, a specific question for large language models, in that I've read a few papers that have kind of tried to fine-tune BERT or GPT-2, for example, on some new data set. And rather than kind of adopting these common practices, they start with a learning rate that's near zero, amp it up to some large value, and then bring it back down. Is there any intuition for why that's a good thing to do, why that's a reasonable thing to do, or is that just like some weird neural network magic?
Yeah, so I actually haven't read those papers myself. I guess I don't have any good intuition for that, at least off the top of my head, for why that might make sense. I think that in general, it makes sense for it to have a larger learning rate for the later layers, because those are probably the things that need to change the most. So maybe when you amp it up, it's really focusing on those later layers. And then after that, in general, decaying your learning rate makes a lot of sense. But I'm not sure kind of ramping up the learning rate to be higher for the earlier layers seems like it could also have a detrimental effect. So I'm not sure exactly what the intuition for that is.
Thanks.
Okay.
Hi, yeah, my question was about like dimensionality and how it ties into transfer learning. Like, for example, if you're doing computer vision, right, like you have your set kernel sizes, but the images are going to be like, if you're adapting to a new data set, you could just have completely different size images or like fewer channels or something. And like, so I guess I was wondering what your intuition was for, like, let's say you're jumping to data set B, which has the images have like half the number of channels, but like twice the actual like resolution. Like, do you, I guess, how does that tie into how you decide to freeze certain layers or like reinitialize certain layers?
Yeah, so one thing that you could do when handling images of different dimensions, when you want to kind of fine tune to images with a different dimension, is to, well, one obvious thing you could do is just to resize it to the dimension that's the same as what the pre-trained model was trained on. But that may be discarding information, or it may be your images are smaller and you don't have a good way to upsample them. I think the most important thing to do is to make sure that especially if you're using smaller images, to make sure that when your network is kind of decreasing the dimensionality of the features, that they don't become too small. If you need to have higher resolution, for example, then the default way to kind of pool or dimensionality may not actually work for the smaller images that you're transferring to. Beyond that, I think that in some ways this is kind of another design choice to see if it works for the higher resolution images or not. I don't think that there's any work that really studies this systematically.
Okay, thank you.
Okay, and then one more question from, sorry.
Yeah. So I want to ask, what size do we expect for the new data set? So can we do transfer learning for full-time learning? And if we can, like, what are some practices you recommend?
Yeah, that's a great question, and actually kind of transitions nicely into the next slide. So these plots are actually from pre-training with a language model. Kind of OMFIT is the name of this paper, which is unsupervised language model, and then fine-tuning. And what these plots are showing is that on the x-axis is the number of training examples in your target task. So on the right you have kind of a larger target data set, and on the left, you have a smaller target data set. And what you see is that the validation error rate on your target task goes down as you have more data. So if you have more data from your target task, then these methods, then kind of fine-tuning works better. And specifically, the orange and the green curve are showing fine-tuning, and the blue curve is showing training from scratch. But if the number of training examples is really small, like if you only have 100 training examples, then fine-tuning isn't as successful with a substantially higher validation error rate than if you had many more examples. So kind of the overall takeaway here is that fine-tuning doesn't work quite as well when you have very small target task data sets. It's most successful when you have kind of a more moderate size data set, but you still don't need something as large as ImageNet, for example, with millions of examples. And so this is also kind of where meta-learning can come in and kind of allow you to be able to generalize better when you have a very small amount of data. And so that's what we'll talk about next. Do you have a question?
Yeah, sorry, I think that's that. I see green, orange, and blue consistently. Can you explain why small number of examples means that fine-tuning doesn't perform well according to these graphs?
Yeah, so what I mean by that is that when you have 100 examples, your validation error rate for orange and green is around 30 to 40, whereas if you have, say, 1,000 examples, then your validation error rate is closer to 10 on this data set, which is the Trek 6 data set, and you see kind of a similar trend. And ideally, we'd like to take this performance when you have only 100 training examples and get it closer to the kind of level that we can perform if you have more data. That said, it is still doing better than Scratch when you have small amounts of data. So there's still a big improvement there, which is good. Okay. So now let's talk a bit about meta-learning, and we'll start by talking about the problem formulation. And I guess a disclaimer is that I'll cover a meta-learning problem statement that we'll consider in this class, which is basically the problem statement that the meta-learning algorithms that we'll discuss will solve. But there are other forms of meta-learning algorithms that solve a different problem statement. So that's kind of, I guess, a disclaimer. There's a lot of things that people have called meta-learning. This is what will be this is the problem statement that we'll be considering in this course. And to start off, I think there's, in many ways, two ways to view meta-learning algorithms. There's a more mechanistic view, and there's a more of a probabilistic view. In the mechanistic view, you can view meta-learning as essentially a deep neural network that can read in data sets and learn from those data sets to make predictions for new data points. And training the network itself uses a data set of data sets, or a metadata set, which itself consists of many data sets. And each data set is for a different task. This is sort of like the mechanistic view that we'll talk about. And then the probabilistic view of this is you can view meta-learning as trying to extract prior knowledge from a set of tasks that allows for efficient learning of new tasks. And specifically, learning a new task uses this prior and a small training data set to infer the most likely posterior parameters. There's kind of, these two views I think are actually both quite interesting and useful. Today we're going to focus primarily on the mechanistic view because I think it's a little bit easier to understand, especially from the standpoint of implementing these algorithms. But we will talk about the probabilistic view when we talk about Bayesian meta-learning algorithms and explicitly connect these meta-learning algorithms to graphical models and learning priors over parameters in those graphical models. Okay, so when talking about meta-learning and the meta-learning problem statement, I'd like to first start with an example. So, and specifically, we'll look at a few-shot image classification example. And the goal of this few-shot image classification problem will be the following. Given one example of 5 different classes, there's essentially kind of a little mini training data set with 5 examples. Your goal is to classify new examples among the 5 classes that are in the training data set. So essentially, your goal is to learn from 5 data points to identify and classify new examples. This is analogous to the few-shot learning problem that you did in the first lecture with the different paintings, where you were trying to classify from 6 examples which painter painted the test image. So this is an example of a few-shot learning problem. And this is kind of the problem that meta-learning tries to solve, or at least few-shot meta-learning algorithms try to solve. And the way that they do this is they aren't going to start from scratch. If you were starting from scratch, you wouldn't be able to train on this kind of tiny data set of 5 examples, of course. And so what meta-learning algorithms try to do is, like transfer learning, they assume that they have some previous data. And in particular, in this example, they assume that they have previous data of other image classes. And that data will be structured just like what we see at test time. It'll be structured into train sets and test sets. And we'll kind of construct these training sets and these testing sets for many different image classification tasks. These will be constructed among a large number of training classes, which will be different from the classes that are used at test time. And the goal will be is to essentially figure out to train a model such that after it sees this training data set on the left, it can effectively classify new examples in the test set on the right. So it's essentially learning how to learn each of these image classification tasks. And then once you kind of learn how to learn these different tasks in the meta training set, then at meta testing, when you're given this new few-shot learning problem, you'll be prepared to solve it because you've solved many other few-shot learning problems. So this is kind of a new task, and it also has a training set and a test set. And you can also, so this is kind of one example of a meta-learning problem where you have these different tasks, and each task corresponds to an image classification task. But you can replace image classification with different regression tasks. You can replace it with language generation tasks. You can replace it with robotic skill learning tasks. Really any kind of machine learning problem can be filled, you can replace these tasks with. So that's kind of an example, and more concretely, the meta-learning problem is the following. Given data from n different tasks, your goal is to quickly solve a new task given a small data set for that new task. So maybe the data set is d-test. And one of the key assumptions here that we're going to use is that the meta-training tasks and the meta-test task are drawn IID from the same task distribution. So for example, there'll be some distribution over tasks P. All of your meta-training tasks, task 1 through task n, are drawn from that distribution, as well as your test task is also drawn from that distribution. And this assumption is really important because that means that after we've kind of trained on this set of tasks, when we're given a new task, we can expect that we'll generalize under the same principles of kind of IID training in supervised learning. Okay. And then like before, like multitask learning and transfer learning, the tasks must share some structure. So if this distribution P is the distribution over all possible tasks and you're just drawing random tasks from it, there's no structure that you can latch onto to learn the new test task more quickly. And instead, what meta-learning aims to do is to kind of find the common structure among all of the training tasks and leverage that structure when learning the new task so that it could learn it with less data than if it were training from scratch. So there are some questions on how this relates to multitask learning and meta-learning. And the kind of main difference is that in multitask learning, you would be given data from n tasks, and you want to just solve those n tasks. You don't really care about solving a new task, leveraging that experience. Whereas in meta-learning, your goal is to potentially solve those n tasks, but most importantly, be able to quickly solve a new task with a small amount of data. Okay. What do the different tasks correspond to? They can correspond to a lot of the things that we were talking about before. So they can correspond to recognizing handwritten digits from different languages. You'll be looking at handwritten digits that look like this and trying to classify handwritten digits from a new language after seeing data from a number of different languages. You'll also be looking, you can also have kind of a spam filter for different users, and your goal is to kind of, given a new user and a little bit of data from that new user, can you learn a good spam filter for that user? You may be interested in looking at classifying species from different regions of the world. Maybe you have a lot of data from a range of different regions, but then you're given a little bit of data for a new region. You want to be able to learn a good classifier for that new region from a small amount of data. And then lastly, it could also correspond to a robot performing different tasks. Maybe the robot has learned 50 different tasks before, and it wants to learn, kind of add a new task to its repertoire from a small amount of data. This is another way to do that. Okay. Now, one other natural question is, how many tasks do you need? What should the value of n be? The more, the better. In many ways, kind of this is analogous to having more data in machine learning. If you have more tasks, then you'll be able to potentially do better on a new held out task. One thing that's different though is that per task, you don't necessarily need a lot of data. You just want to have a lot of tasks to cover a broader distribution. Okay. Any questions on this before we go over some terminology?
Yeah, my question is a few slides back. It was, yeah, right there. Okay, so when it's classifying the new examples, is it just giving it like one, like, is it just, since it can't tell us whether it's like a lion or a bull, will it just give us like a 1 or 0 that corresponds to the training data? Like,
so yeah, so at meta test time, you'll be given these 5 images in green, and you'll also be given kind of labels associated with each of these images, 0, 1, 2, 3, 4. And then your goal will be, given these kind of test images, you want to learn a classifier that basically tells you that this lion corresponds to a label of 2, and this bull corresponds to a label of 4.
yeah, makes sense, thanks.
My question is about, you said like the number of tasks required for meta learning, right? So what is the minimum number we should at least have to even consider a meta learning problem? Like, is it like a 5 or 10 should be sufficient, or like you need like 25, 30, or like minimum number of tasks?
Yeah, that's a good question. I would say more than 1. And I think that basically the more tasks you have, the more effective it will be at generalizing to a new task. If you only have a few tasks, then it may not be able to kind of generalize and kind of find the common structure from those tasks in a way that allows you to do well. But really more than 1 is kind of what it looks like. And if you only have 1 task, that looks a lot like transfer learning.
So like if you're 10 tasks should be like minimum, we can think like, okay, this might be a meta learning problem to start with, like 10 or 15 kind of thing.
Yeah. And then in the homework, you'll be looking at the Omniglot dataset, which actually allows you to construct on the order of 1,000 tasks. But I've also seen meta learning be successful when you only have like maybe 50 tasks, or maybe even a little bit less than that.
So other question, like in multitask learning, what is the maximum number of tasks? I mean, I can see like multitasking you can do at least 2 tasks to start with, but like how maximum you can go in multitask learning, like where you can start seeing the performance might be great. Like if you have like lots, like 1,000 tasks, it may not work.
Yeah, it really depends on the problem setting, how many tasks you start seeing benefits or not. It's really problem dependent. It looks like there is also a clarification question in the chat, which is what's the difference between X test and D test? I'm kind of calling this these examples X test, and then these are within some data set D test. So this is basically, so for this task, for example, I would call this kind of D train for task 1 and D test for task 1. And I think that answers the question.
So I guess just to understand the idea of like meta in this, like what we're trying to do, is it like we have like one task or like a multiple task, which is like T1, T2 there. And then like, we give it the meta, which is these 5 images, and then we have the input, which is those 2 images to classify, and then it needs to use that meta or like refer to that to like make a prediction. Is that kind of like where the meta term is like being used?
Yeah. So we'll get a better understanding of kind of why it necessarily corresponds to meta learning when we talk about algorithms. But one perspective that you could take here is that, like for each task, for example, you're trying to learn from a data set and be able to generalize to the test data set. So each of these tasks corresponds to a learning problem. And then when you're considering all of these tasks and trying to be able to quickly learn from any of these training data sets, then you're essentially learning how to learn each of these tasks. And so that's sort of where meta learning comes from.
Okay, so when you say like we want to like be able to like learn a new task quickly, is that like, so a new task would be like if we get like an image from each of those classes and then like we sample some random 2 images from like any of the classes, like that would be like a new task. Like, is that like
yeah, exactly. So this is
like this corresponds to a new task, and your goal at test time is to learn this new task with this small data set.
Okay, yeah, got it. Yeah, thank you.
Hi. So I heard in NLP, the learning hasn't converged in terms of some past X4 and natural questions. Similar, is it true for vision as well, where the learning, just because the number of metatasks you can use, it's just not converged. You can just include as many tasks and as much data for each task.
So are you asking if you include more tasks? Like I guess I'm not sure I understand the question.
The question is, if you just, I think this is a riff of a previous question where how, the maximum number, so to speak, has the learning converged? Have people found that, okay, adding more tasks or more data to any task for this particular task is not beneficial to the error rate?
Yeah, so I think that, the question is kind of like, what is the maximum number of tasks until you really start seeing it converge? In the Omniglot dataset, which we'll talk a bit more about later, where you have around 1,000 tasks, I think in that setting, the validation performance starts to converge towards the training performance. And that's a setting where it does seem like you have enough tasks in that setting. Then again, it is also still very problem dependent. If you have a very broad data distribution, then you'll need more tasks to cover that. Whereas if you have a very narrow task distribution, then you may not actually need a very large number of tasks to adequately cover that.
Okay, thank you.
I'll go through, I want to kind of quickly also go through a bit of terminology, since this may also answer some of the questions, and then I'll take some more questions. So as I mentioned before, kind of each of these green boxes correspond to training data sets for individual tasks. So this might be, maybe this is task I, then this box corresponds to the training set for that task I, and this red box corresponds to the test data set for that task. This is kind of, the training and test data sets are distinct from what's called meta training and meta testing. So in many ways, you're actually going to be using these individual meta training test task data sets, or sorry, the test data sets for different meta training tasks. You'll be using this and actually training with these during the meta training process. And sometimes to kind of make a better distinction between meta training and meta testing and training and testing, people instead call each of these green boxes the support set and the red boxes the query set. And we'll probably use both of them interchangeably, although in practice, I think I'll typically use the training set and the test set a bit more frequently. And then when we talk about few-shot learning or K-shot learning, like one-shot learning, five-shot learning, what this means is that we're going to be learning with K examples per class. Or if we're in a regression scenario, we're going to be using K total training examples for learning. So kind of K-shot means you'll be using K examples. And then if you're doing n-way classification, then you're choosing between n classes. So you're basically classifying among n things. So one kind of question for you based on this terminology is, in this above example, what would the values of K and N be? And you can answer this in chat. So K is the number of examples per class, and N is the number of classes. Great, so it looks like people are entering the correct answer, which is K equals 1 and N equals 5 for this above example, because we have one example for 5 different classes. Typically, the value of 1 and the value of K and N, you often keep it consistent among meta training and meta testing, but you could also train on a larger number of N or variable K, and then test it on variable K and variable N.
So there is like few-shot learning. Does that mean basically that when K is small, like it does better or something? I don't know. I'm just curious if you can talk about that a little bit.
Yeah. So the problem of few-shot learning is basically when you want to learn with a small amount of data. So basically when K is small, then you have a small data set, you want to learn from a few examples. Okay, do you have a question?
Yeah. Is there some more formal definition of what a task distribution is? Like, do they have to have common classes, or what's the definition of a task distribution?
Yeah, I think that there isn't really a formal definition of the distribution over tasks. I guess before I gave a formal distribution of what a task is, which corresponds to the kind of the data generating distributions of basically P of X and P of Y given X. And you could potentially, these are kind of the true distributions underlying the data, and you could view maybe these true distributions are parameterized by phi in some way, and then you could formally view a distribution over tasks as being equivalent to a distribution over the parameters of those data generating distributions. In general, though, it's a bit tricky to think about sometimes because sometimes these data generating distributions aren't even necessarily have a parametric form. And so it's a bit tricky, and it's a little bit dependent on the particular domain that you're in. One example of where you can parameterize a task distribution is maybe different tasks correspond to different sinusoids, where maybe they're all different, a family of sinusoid functions where you're trying to regress to the value of the sinusoid given the X value. And then maybe the parameters would correspond to like the amplitude of different sinusoids or the phase of different sinusoids. And there you might actually be able to explicitly represent the distribution over the data generating parameters. But in practice, it's a bit tricky to do that because we don't really know the parameters underlying the image formation process, for example.
Right, so kind of the definition of a task distribution can be as broad as possible. Like if there is a task distribution that includes all the tasks possible.
I guess it's not clear. You could have something that conceivably covers all the tasks possible, but then that may, if P of X is like truly random, then that may not actually be that useful or interesting, because typically for like image classification, for example, we're interested in natural images, and so P of X we would want to kind of cover the distribution over natural images and not include random noise or white noise, for example.
Right. Thanks.
Hi, I have a general question. I wonder how the meta learning is robust or in some extent compared to other conventional supervised learning. For example, if there are some wrongly labeled images in the image classification example.
Yeah, so I think it's going to depend on the algorithm that you use. I think the different algorithms may have different robustness properties.
Okay.
I'm also not aware of any works that explicitly study that, although there was actually a course project last year that looked at if you could essentially meta-train a model to be robust to label noise. So you could look at the course projects from last year if you're interested in that.
Okay, thanks.
Hi, yeah, I'm still trying to tease out the difference between meta learning and transfer learning in this case. So it kind of looks like, if I were to kind of think in my head, the meta learning step, the meta training step, kind of looks like you're using like an ImageNet pre-trained model, but just kind of breaking it up into different tasks instead.
Yeah. So here's a summary slide that kind of goes over it to some degree. So in transfer learning, the previous data that you're going to have will be typically in the form of a single task. Whereas in meta learning, you're going to actually have a stronger assumption and assume that you have these different tasks and that the different tasks are drawn from the same distribution as your downstream task. One way that you could view this is that meta learning algorithms are actually going to be explicitly optimizing for the ability to learn a task within that distribution. Whereas transfer learning approaches tend to be a bit more ad hoc, and they, for example, in fine tuning, will just kind of train on one task and then fine tune the weights on another task. Does this answer your question?
Well, I guess I'm thinking, what qualifies as something, a task being distinct from another task? I guess.
Yeah, I guess.
So yeah, in the image recognition example, it is a good point that basically you could construct these tasks from a single data set, from like the ImageNet data set, for example. And this is actually quite common in the few-shot image classification literature. One thing that is important is that you have to actually construct those tasks rather than just having a single monolithic task in meta learning, because you have to be able to, and you have to construct them in a way that it is from the same distribution as your test task. But it is true that basically these tasks could be constructed from a data set that's quite similar to the data set that you use for the source task in transfer learning. Okay, maybe we'll move on to.
Hi, I had a question about the slide with the terminology on it. I'm still, I guess, a little bit confused. So is that first green box, is that equal to D sub I of the training set, or is that just one example from D sub 1 of the training set?
Yeah, so this first green box, this kind of green box right here, this would be like D sub I for like task 1, so maybe I equals 1. And then this whole box would be D sub I for I equals 2. Okay. Does that answer your question?
Yep, thank you.
Great. I think we'll type out her question in the chat. In the meantime.
So I was just wondering, why do the tasks have the same number of classes, like the fixed n? Does it help? Because it doesn't look like the classes are like similar across the tasks.
So you're asking why have a fixed n for different tasks?
Yes.
Yeah, so in practice you could have a larger, you could have kind of a varying n for different tasks. You do want to have a scenario where the test task that you're the kind of the meta testing task has a value of n that's at least as kind of that's no larger than any of the n that you saw during training, but you can have variable n.
Okay, thank you.
And then asked in the chat, is task grouping considered a challenge? We see task grouping is a challenge in multitask learning, and I was reading a recent paper that comes up with a task grouping framework to deal with it. Yeah, so different tasks may be more similar to one another. Like you may have, you could construct a task distribution that has medical images and natural images, for example, and it may actually be helpful to learn a grouping of those tasks if you find that your algorithm isn't finding common ground between those two sets of tasks. And that's definitely a challenge that people have looked at, especially when you observe negative transfer between different sets of tasks. Cool, and then one more question from.
Right, what do we have
what to do if we have varying k for each task.
Yeah, so you can also have varying k, and we'll talk about this a bit when we talk about algorithms. So feel free to bring that up again when we talk about algorithms. I'll try to cover it when we talk about black box methods. Okay, so let's move on to algorithms for the sake of time. So to recap the problem setting, I guess we went over this slide a bit, but in multitask learning, you're trying to solve multiple tasks at once. In transfer learning, you're trying to solve a new task after solving a source task. And in meta learning, you're trying to quickly solve a new task given data from a number of previous tasks. In both transfer learning and meta learning, it's generally impractical to access the source task or the previous meta training tasks, just because you often don't want to retrain on that data, or maybe you don't have the space to retrain on that, or just it's really slow. And in all of these three settings, the tasks must share some common structure in order to get benefit compared to just training these tasks from scratch. Okay, so now let's actually talk about a general recipe of meta-learning algorithms and then one instantiation of that. And kind of, I guess, first let's talk about a general recipe for evaluating a meta-learning algorithm. And in particular, I want to kind of highlight the omniglot dataset that we've talked about a little bit up until now. So the omniglot dataset has 1,623 characters from 50 different alphabets. And here's kind of an example of what the data looks like. So it has alphabets like Hebrew, Bengali, Greek, Futurama. And for each of the characters in each of these alphabets, there's 20 instances that are handwritten of each character. And so one thing that's interesting about this data set is that it has many different classes. So it has more than 1,000 classes, but it only has a few examples per class. So only 20 instances per class. And in some ways, this is kind of like the transpose of MNIST, because the MNIST data set, for example, has 10 classes, and it has like a very large, it's like 1,600 or something like that, a very large number of instances per class. And I also think that this sort of data set is actually more reflective of what we see in the real world. We don't see like 1,000 different instances of forks and spoons and 1,000 different water bottles and so forth. We see much more diversity in the objects that we see and in the words that we see and so forth, but we only see each instance a few times often. So that I think makes these sort of data sets quite appealing. And the omniglot paper proposed by Brendan Lake in 2015 actually proposes two different kinds of problems, both discriminative problems where you want to classify the character from the image, as well as a generative problem where, given maybe one or a few examples of a character, you want to generate more instances of that character. Although to date, the discriminative version has been much more popular and used much more widely than the generative version. And then kind of the initial few-shot learning techniques before this paper and also around the time of people were modeling characters were actually based off of Bayesian models and non-parametric approaches. And Brendan Lake showed that these approaches can actually be, these kinds of approaches can actually be quite good at modeling these simple characters, but they are harder to scale towards natural images and kind of larger data sets and more complex data sets. And so that's why we'll be focusing on more approaches based on deep learning in this course. And then beyond the omniglot data set, which in many ways is actually already is fairly saturated performance, people have used other image recognition data sets like ImageNet and different variants of that, CFAR, CUB, and SLEB-A. And then beyond image classification, there also are a couple other benchmarks that I'll mention in case you're interested in using them for your course project, such as predicting the properties of different molecules and predicting the pose of different objects. Okay, so this is kind of some data sets that people have used for evaluating meta-learning algorithms. And then now to start to talk about different approaches, I actually want to present a second view on the meta-learning problem. And in particular, I'll do this in relation to supervised learning. So one way to view the supervised learning problem is that we're given an input X, like an image, and an output Y. We want to learn a model that predicts Y from X. And we do this with a data set. Now, similar and analogously to this, we can view the meta-supervised learning problem as something where we're given a data set that has K examples and a new data point X test. And given this, we want to predict the corresponding label for X test. And so you can view the meta-learning problem as something that essentially takes in a data set and a new data point, learns something from that data set, that training data set, and makes a prediction that hopefully generalizes to this new test data point to predict Y test. And the way that we do this is analogous to supervised learning. We have data, but in this case, our data corresponds to a data set of data sets, where each data set has more than K examples, so that you can sample K to be used in the training data set and at least one to be used to measure generalization here. Now, you might ask, well, we already talked about the meta-learning problem. Why is this useful? Why are you telling me this? This view is actually useful because in many ways it reduces the meta-learning problem to figuring out how we might want to design this function H and how we want to optimize this function H. So essentially kind of a general recipe for meta-learning algorithms is to choose a form of this function that basically takes in a data set, learns something from that data set, and makes predictions on new data points. And then second, choose how to optimize the parameters of this learner with respect to some maximum likelihood objective using the meta-training data. So this is basically kind of the general recipe for meta-learning algorithms. We'll refer to theta as the meta-parameters in the sense that they're the kind of parameters of this learner here. And this function will often kind of refer to as the learner in the sense that it's learning something from a data set and applying what it's learned to predict the label for X test. Okay, so this is the general recipe, and really the simplest way to instantiate this is what I'll call black box adaptation, where the key idea is to kind of train a neural network to represent this learner that takes as input a data set and outputs a set of parameters, and then predicts test data points with a model with those parameters. So in some ways you can, I guess before I had called H a learner, we could also call this a learner, where it's taking a data set and basically outputting a new set of parameters, analogous to how things like SGD take a set of initial parameters and then produce a learned model. But in this case, F isn't going to represent SGD, it's going to represent just a black box neural network. So we're basically going to be training a neural network to take as input data and output a set of parameters such that that set of parameters generalizes well to new data points. So in this case, here is dtrain, here is the data point in dtest, and we can train this with standard supervised learning. So we can take our meta-training data set and feed in the data into this neural network, have it produce a set of parameters, and train it such that with those set of parameters, it makes accurate predictions. So what it looks like for standard supervised learning is we sample a task, we sample, we have the training data set for that task, which produces phi, and then we train it such that this network phi this network G with parameters phi can accurately predict labels based on that for that task. Yeah, so you can also view kind of this loss as how well this set of parameters phi does on the test set. And then from that standpoint, you can view this meta-training objective as something that has your model that takes as input a training data set, produces a set of parameters based on that training data set, and then is trained such that that set of parameters generalizes to a test data point. And this optimization is done across all of the tasks. So any clarification questions on how this works?
Yeah, a couple of questions. On this slide, I'm just confused as to whether we're allowed to go back to TI, if TI is a part of the meta training.
Yeah, so you do this, this is kind of what happens during training is you have, like we talked about before, you have a trained data set and a test data set for each task. And you sample different tasks, you pass those into your model, that produces a set of parameters, and then you evaluate the generalization performance of that set of parameters. And then at test time, you no longer have any of the meta-training data set, and you're given a data set for a test task. This is kind of the trained data set for this new task. You pass that into the model, and that gives you a model that generalizes for that test task. But you don't need any of the meta-training data for to do this at test time.
My question was about the TI in the bottom right of the slide. Sorry, could you go hover over that again?
Yeah, so this TI, this is a sum over all of the tasks in your meta-training data set.
Okay, fine. And my next, I have one more question, if you have time. If you could go 2 slides prior or 1 slide prior. Maybe one more. Okay, well, it's more about the K and of the future of the K and N basically. Maybe I'll just follow up on Piazza because it's most about the slides.
Sounds good, yeah.
I have a question on the last slide that you presented.
Sure.
And essentially, I'm wondering conceptually why we introduce phi I as opposed to treating this as a traditional learning problem where, in addition to your X test, you're also priming the network with the support set that corresponds to, or the support set for the task that corresponds to the training sample or the testing sample that you're getting. I don't know if that makes sense.
Yeah, so you could, in some ways, you don't necessarily need to represent phi separately. And we'll talk about a situation where phi doesn't actually correspond to a huge parameter vector in a few slides. Yeah, so you don't need to necessarily represent that. In this case, in either case, though, you are taking in the support set right here. These are kind of your support data points, and then passing in a new data point here. Does that answer your question?
Sort of. I think the question was more why phi I, but I guess that mechanically you just said that it doesn't make a difference. So
we'll also talk about it, basically, maybe ask a question in a few slides if the few slides ahead don't kind of clarify it. One important thing I will say is that it's important that this phi I depends on I, because this is going to be different for different tasks depending on the training data set that you pass in.
Yes, just wanted to clarify. So, or some technical things. So, like, F data is a neural network that predicts like another neural network's parameters, or like a task network. And then, when we get those parameters, do we set that as the initial parameters of the network of G, and then we train G to make those parameters optimal, or like so X like predicts Y almost perfectly, and then do we do supervised learning to get the predicted phi I to be the optimal phi I, kind of like that, and then backpropagate like that and repeat?
That's close, although it's not quite that complicated. You basically have a neural network that takes as input the trained data set and outputs the parameters for this other network. You don't need to do any additional training on phi. What you'll be doing here is basically it outputs the parameters of another neural network that is that corresponds to this neural network right here. And then when you do this kind of meta-training optimization, you're optimizing over the parameters theta of this model right here. And you're basically optimizing this model so that it can effectively produce parameters for these different tasks.
Oh, okay, so I guess like the gradients would kind of be passing straight directly through theta rather than through phi.
Yeah, so the gradients will pass straight directly through phi into theta.
Okay, and then for phi I, does that have to be the same for all tasks, or like I'm guessing like that has to mean like whatever task we have, like it has to be the same architecture of neural network that G would be.
Yes. So in this case, you would want it to probably have the same neural network G for the same architecture for different tasks, and yeah, this will, but you'll have different parameters of that architecture for different tasks.
I see. Okay, cool. Thanks.
Hey, so judging by what you said, it seems like we're distinguishing between the meta parameters, I guess theta, and the task-specific parameters that are output by the planar, which is phi I, right? Yeah. I was wondering, so since you're training the whole thing with just this ingredient descent straight to theta, is there like a two-step kind of accommodation, because like you can compute the gradient of loss with phi I, and then I guess that itself depends on theta. So you can essentially again to get the gradient for theta. Is that how it is?
Yeah, so when you compute the loss with regard to theta of this objective, for example, what you'll get is you'll get something that corresponds to basically dl d phi I, and then you'll get d phi I d theta, just with the chain rule. That will allow you to get gradients for theta for each of the tasks, and you'll average those across all of the tasks.
Cool, thanks.
Yeah, so while training this model, would you run it on all the tasks and then update the gradients, or would you wait for one task to converge first? Like, how would you do that?
Yeah, so in practice you'll sample a batch of tasks and like kind of a mini batch of tasks, and you'll average across that. So actually, I'll just go through the algorithm right now. So what this looks like is you'll sample one task or a mini batch of tasks. You will sample disjoint data sets, detrain and detest, from the data that you have for that task. So maybe the data that you have for this task looks like something like this. Then you'll basically put this into a detrain and a detest. Then you'll compute phi I from the training data set. Then you'll update the meta parameters using basically the gradient with respect to theta, evaluated with respect to how well phi I does at predicting new data points in detest. If you have just a single task that you sampled, then this gradient will just be with respect to that one task. If you use a mini batch of tasks, then you'll basically compute the gradient for each of these tasks, compute the meta gradient with respect to the meta parameter theta for each of the tasks, and use that to update theta. And then you'll iterate this process, iteratively updating theta based on the task that you sample.
Yeah. So my question is, in this particular setting, the model is basically trying to learn a kind of pattern matching, right? Like it's not really understanding what really that image is. All it's trying to do is in the test set, what is this particular image closest to in the given task training set, right? It's not really trying to understand what that image is or like what are the deeper level features of that image is, right? It's just trying to match what is it closest to in its given training set.
Yeah, so when you have like kind of in this case, like a four-way classification problem, then a kind of reasonable strategy is just to find something that kind of matches, well, how does this like image look like in comparison to each of the examples in the train set? We'll actually talk about approaches that specifically try to do this kind of matching process in a few lectures when we talk about non-parametric meta learners. One thing that I'll emphasize is that if you're doing classification, this strategy might work, but if you have regression tasks or motor control tasks or something, then kind of the general principle of trying to take in a data set and learn something from that data set that generalizes maybe a little bit different than the matching process that you just described.
Right. So just from my understanding, that's what we are trying to do, right? Like we are not really trying to get a deeper understanding of what these images are, right? We are just trying to,
Yeah, so we're just basically trying to
be able to generalize, be able to produce an image classifier that can classify among these 4 classes in this example. We're not trying to generalize beyond these 4 classes or beyond what's in the training data set. And then one more question before.
Are there any trade-offs besides complexity if we wanted to make phi robust to permutations in the support set?
So basically you're saying that if you basically change the order of the examples in the training data set, like are you asking about how you can make it robust to those permutations?
Yes. Or
Yeah.
you could build a more complex model, I suppose, but is there anything else that you should think about before jumping ahead and doing that?
Yeah, so we'll talk about that in 1 or 2 slides. Cool. So one challenge that comes up with this approach is that outputting like a lot of neural network parameters doesn't necessarily seem very scalable because you have to have a neural network output all of those parameters. And so one idea for approaching this, and this has actually been one of the more common ways to approach black box adaptation approaches, is to not output all the parameters, but only output some of like the sufficient statistics that you need. And what this looks like is instead of outputting a phi I, you instead output this kind of hidden vector H. And I'll use H because it's analogous to the hidden state of a recurrent neural network. And this represents kind of contextual task information. And then this neural network G is going to be basically a combination of this contextual information H, and then some fixed parameters theta G that are the same for all of the different tasks. And so you may just have another neural network that has these parameters theta G, and then also takes as input task-specific information and uses that to classify the images in dtest. And if you recall when we talked about multitask learning, where we had this vector ZI that kind of encapsulates task-specific information, this is also kind of pretty similar, where this HI can capture information about that task and tell you what task you're trying to be performing, where theta G would then correspond to the parameters of this network. Yeah, and then in this case, when you optimize over the metaparameters, you'll optimize both over theta G as well as the parameters of this network that produces HI. You may also have some amount of parameter sharing where theta G may also be kind of a part of this network on the left. Maybe like these encoder parameters are also kind of the same as how you encode the input here. And then you get something that looks like a recurrent neural network where it's just taking in data points and then also taking in the test data point and making a prediction. Okay, and then kind of the most general form of this is something, just a model that takes as input the training data set and the test input and produces the corresponding label. Okay. Now, one natural question is what architecture should we use for this model F theta? There's a few different kind of approaches. One is to use an LSTM or a neural Turing machine. These are basically different architectures that incorporate some amount of memory into the neural network. You could also use an architecture that is feed forward. It basically takes as input each of the examples in a feed forward network, produces some embedding R, and then averages that embedding R to, and that R is kind of provided to another network, another feed forward network that tells you information about the task. I'm curious if anyone has thoughts on why a feed forward and averaging architecture might be better than a recurrent neural network.
I think that the memory of an LSTM or a recurrent model is most useful when you have a bunch of temporally displaced data, and here you're not necessarily actually capturing any sort of notion of temporality, since it's just a bunch of discrete data points.
Yeah, so the data that you're receiving in a supervised learning problem may not have any temporal structure. And then also, as mentioned in the chat, and also what was mentioning earlier, it doesn't matter what order these data points are in. And if you kind of permute the ordering, then you should get the same output, right? And so this feed-forward architecture is actually permutation invariant for the data. You'll get the same embedding as a function of the different permutations of the data. And so that encodes this kind of nature about most data sets that they are permutation invariant. Of course, there is also data that sometimes has temporal structure, and in those cases, things like RNNs might be better. And then there's also other external memory mechanisms. People have used temporal convolutions, and these kinds of architectures tend to have shown strong performance on different problems. So for example, this model that uses attention and convolutions is able to get around 99% accuracy on 5-way omniglot and around 97% accuracy on 20-way one-shot omniglot. Okay, so pros and cons. One benefit of this approach is it's very expressive. It's also easy to combine with a variety of learning problems. So we'll see later in the course how you can combine this with a reinforcement learning problem. One downside is that it's RNNs and these architectures can be fairly complex, and they also have to learn how to process this data and learn from this data from scratch, basically. And so it could be a challenging optimization problem. And you'll find in your homework that it can be a bit finicky based on different hyperparameters and different choices, although we'll hopefully provide good hyperparameters so you don't need to do too much searching. And as a result, it tends to be fairly data inefficient in terms of the amount of meta-training data that it needs. And then on Wednesday, we'll talk about what happens if we treat this as an optimization problem instead of kind of a black box neural network problem. If people want to stick around and ask more questions, you're welcome to, and I'll answer them. If not, I'll see you all on Wednesday.